Hello, bro. Can you hear me?
Can you guys hear me?
Yes, I can hear you. Your video is not on.
Yeah, my camera has gone bad, so I haven't been able to figure out why.
Gotcha. When are you coming back to there?
No idea.
No worries.
Okay, so here's
Hope to
everybody
see you
joining.
soon. Yeah. Uh, I think there is one more minute for the
Yeah.
class to start.
Okay, wait a few more seconds, so maybe a couple more will join, and then we will start.
Sure. Yeah.
All right, let's begin. So, good afternoon, everybody. And this week we will be going over estimating statistical models for data. So maximum likelihood estimation, and specifically we'll look at expectation maximization. The problem we are dealing with is that of estimating distributions from data. For example, the roll of a dice. So if the dice is loaded, then not all numbers are equally likely. And so let's say you roll the dice a number of times and you get a histogram of this kind, which says that the number 1 turned up n1 times, 2 turned up n2 times, and so on. So the distribution of the dice, I'm sort of inappropriately calling it a multinomial here. The correct terminology is a category distribution, where there are 6 categories of outputs in this case, and each of them has a probability. And this histogram is the outcome of draws from this probability, because that's what the rolls of the dice are. And our problem is to determine the probability distribution for the dice from the collection of outcomes. So this is a problem of estimating distributions. In this case, multinomials, or more precisely, category distributions. So also, let's say you observed a typical real-life phenomenon and got a large number of readings, and you plotted a histogram, and you got a histogram of this kind. Then if you wanted to determine or estimate what the distribution, the natural distribution of these data, you'd fit a model such as a Gaussian to it. If it was a Gaussian, the mean and the parameters would be the mean and the variance, and we try to estimate these parameters. Once again, this is a problem of estimating the distribution of a data. So that's what we're going to be looking at. Our agenda for this lecture, the next one, we're going to be looking at generative models, fitting models to data, and why we cannot have closed forms often, how we will deal with missing information, and how expectation maximization is a solution to all of the world's problems. So let's begin. What is a generative model? A generative model is the model for the probability distribution of some data. For example, the category distribution or the Gaussian. All of these are generative models. Now, why do I call this generative? Because underlying this model is a generative story for the data. The computational equivalent for this would be that there's a model which, when excited through some random seed, generates a number of generates samples. And so when we learn a generative model, we are speaking of learning a model that can be used to generate data with a distribution similar to that of a given data X. So the typical setting is that this box would take in random seed and outputs random samples, and these samples are going to look a lot like your training data. Now, once you look at this, there's a natural question: where did the seed come from? That's something we are not going to address over here, but then really it's turtles all the way down, because the seed itself is the outcome of some random process, which typically needs some random excitation, and so you can recurse it. This is a problem that we don't deal with in this lecture, in this course. But if you hop over to some of the more advanced lectures on statistical modeling or even diffusion models over in deep neural networks, that's something we do address. So anyway, getting on. So here are some simple generative models, like the category distribution, or the inappropriately termed multinomial probability mass function, like the roll of a dice. Here, the random process has a finite number of outcomes. For example, in the case of a dice, there are only 6 outcomes. Each of these outcomes has a probability. And so this probability distribution can be represented as a table of probabilities, because there are only a finite number of outcomes, and each of them has a probability. You can also have something more complex, where the number of outcomes is still discrete, but infinite. For example, how many seconds do you have to wait for the next bus to arrive at the bus stop? So you could wait 1 second, you could wait forever. So the number of possible outcomes over here is not finite, but it's discrete. And in this case, because the number of possible outcomes is infinite, you cannot use a tabular form for representing the distribution. You need some kind of a formula, like the Poisson distribution, which gives you the probability for the outcome taking some value k, with the formula given here, which I won't explicitly get into. Just the idea that as the number of possible outcomes increases, when it becomes very large, you cannot just use a table, you will need a formula. Now, these are discrete random variables, in the sense that the variable can take one of a discrete set of values. The dice can take one of 6 discrete outcomes. Wait times in seconds for the bus, it can take discrete values again: 1 second, 2 seconds, 3 seconds, 4 seconds, and so on. Now, the finer kind of data are where the data are continuous valued. And in this case, again, we no longer speak of probability mass functions, we speak of probability density functions, like the Gaussian. And we're all familiar with the Gaussian, the famous bell-shaped curve, which has the formula over here, which says that the probability that a random sample from this distribution will take a specific value V is given by this formula over here. It should be V. It's a constant times e raised to minus 0.5 times x minus the mean times the inverse covariance matrix times x minus the mean itself. Again, everybody's familiar with the Gaussian formula. We'll see it again. Just the idea that this is a generative model. The Gaussian, the Poisson distribution, the multinomial, all of these are generative models which have a story behind how the data are generated, that they are drawn from these specific distributions. So when I'm speaking of learning the distribution for a data, we are really speaking of learning what the distribution is. But the thing is that you can never really know what the true distribution of a data is. These are going to be very complex. So what we typically do is to assign some mathematical form to the distribution. So we have a model for it, which I'm representing as P of x semicolon theta. Theta represents the parameters of this function. And so this is the probability distribution model with parameters theta. Now it's very unlikely that the true distribution for any random variable is actually going to follow this model. But nonetheless, by an appropriate choice of theta, you can make the difference between this model and the actual distribution of your data arbitrarily small. And so our objective is to try to learn this theta such that the resulting distribution P of x semicolon theta best fits the observations that you've got, or in alternate terms, it's as close as possible to what you believe the true distribution of the data to be. So when we actually estimate these distributions, we're going to estimate these theta to fit whatever observations we've got to learn the distribution from. And we will hope that in the process, it also represents data outside of whatever training set you've used to learn the distribution. Now, this is all at a very high level. So let's get into any questions. I know this was kind of fuzzy, but any questions so far? We'll get into the details. None? Okay. So here's one. Let's say you have a loaded dice and you want to determine the probability distribution for the dice. So you roll it a number of times and you plot the histograms for the outcomes. And then along comes some oracle and says, the actual probability distribution for the dice is one of these two guys, the blue one or the green. Then based on this histogram, which of these two do you think is the actual distribution of the dice? Anyone? Based on this histogram, which of these two possibilities? The green? Why would you say it's the green? What is your rationale behind saying it's the green one?
It matches the distribution more similar than the blue one.
So how do you say matches?
Like I see the ups and downs in the histogram of the blue compared with the original one, and I see it doesn't match as much as it matches with the green. The green matches very similarly to the ups and downs of the original one compared to the blue one.
So the ratio of populations within bins is similar, right? Okay.
Correct. Yeah.
How about this one? Then, so here again, the left shows the histogram of a collection of observations, and I decide to model it as a Gaussian. The Gaussian has some mean, mu, and variance sigma squared. And so for different choices of mu and sigma square, I get different Gaussians. And then along comes my oracle and says that the distribution is either the red or the green or the yellow. Which of these three would you choose? Which of these three do you think is the actual distribution of the Gaussian? Red. Again, why?
It looks like it has a similar mean and variance.
It has. So when you're doing all of this, you're making an assumption, right? Peak and spread are similar. You're making an assumption, right? What is that assumption? How do you define the fit? And what is the assumption you're making? It looks similar, right? So to say, when you say it looks similar or fits better, we have to define fit. And so our assumption first is that these data are drawn from the underlying distribution, valid assumption. But then this second assumption over here, this one here, this is the key hypothesis that we always work with. And the hypothesis that we work with is that the world is a very boring place. Nothing unusual ever happens. And so if the world is a boring place, then what can you say about this histogram of samples? Is this histogram of samples going to be typical for the distribution or atypical? What would you say it was? It's going to be typical, right? Because the world is a boring place. Unusual things don't happen, right? And so we are working off the world is a boring place hypothesis. And the consequent assumption is that the distribution has a very high probability of generating this data. This is an assumption. It's not necessarily true. It's based on, again, this hypothesis that the world is boring. And so when you chose one of these three as the distribution for this data, you chose the one implicitly as the one that had the highest probability of generating this data. Now, what do we mean by having the highest probability? We can put math to it, but at a very high level, it means that it assigns high probabilities to things that are frequent and low probabilities to things that are infrequent. And this can be quantified. This assignment of probabilities, the boringness of your data, can be quantified. So again, the assumption here is given a large number of distributions, we are going to assume that the distribution that's most capable of generating this data is the true one. And that's because the world is boring, right? Of all the possible things, the one distribution for which these data are very standard, very typical, that's the one that I'm going to choose. Does that make sense?
Yep.
Yes.
So the world is boring hypothesis, right? And so that's basically we work with. Now we can put math to it. Suppose you roll dice and then you get these outcomes, one occurs once, two occurs twice, and so on. Then the probability of generating n1 ones, n2 twos, n3 threes, n4 fours, n5 fives, and n6 sixes is going to be some constant times the product over all outcomes of the probability of the outcome raised to the number of times it happens. Because the probability of seeing n1 ones is the probability of 1 raised to n1. Because we are assuming, again, the assumption here is that all of your observations are independent. And so we are going to, this is the probability of the observations you got. And we are going to try to determine the probability distribution for the dice, namely these p-values, that maximizes the probability of the data that you just saw. Now, this is an ugly multiplicative term. So we typically sort of take a logarithm of it because a logarithm is monotonic. Something that maximizes x also maximizes log of x. And so if you apply a log to this, the log probability here simply becomes the log of this constant plus the sum over all possible outcomes of the log of pi raised to ni, which is the same as ni times log pi. And this is what we must maximize. So, okay. Is it sufficient to just say that I'm going to maximize this, or do I need to have say something else? I'm going to be maximizing these with respect to the p's. What else do I need to have here? Anyone? Is this complete? Okay. If I keep increasing p's arbitrarily, will this continue to increase or not? Have I lost you? Are you guys here? Yeah, okay. The sum of what, Akanksha? The constraint on p, right? Otherwise, you can just say I can make this p infinite, and that's going to maximize this term. So you need an additional term. And how would you impose that constraint, Akanksha? How would you impose the constraint? Anyone? You just use a Lagrangian, right? So you actually need to do plus summation plus some lambda of summation p minus 1. So because summation p must equal to 1, summation of p minus 1 equals 0, that would be our constraint. You have to add that additional Lagrangian constraint over here and then optimize. And if you optimize it, you just get this classic formula that you always learned in high school, that the probability, your best guess for the probability of any event, any outcome, is the number of times that outcome was observed divided by the total number of observations. So this, it turns out, your maximum likelihood estimate is the very well, familiar estimate that you always knew of, which is obtained from counting. So does this make sense so far? Okay. No. All right, guys, just respond. Same thing
Yes.
with Gaussians, right? Suppose I have a bunch of independent observations, x1 through xn. Then the probability of my training data, which is the joint probability of all of my data, is the sum over all, the product over all of the observations of the probability assigned to each of the observations by my model. Again, maximizing this guy is going to be hard because of this product term. So we will maximize the logarithm of this one. And so when you maximize the log of that, you're going to get some constant minus, the log of this, which simply becomes the log of the determinant of the covariance matrix. The summation is over all of your training instances. Plus, and again, the log of an exponent is just the argument of the exponent, which gives you x minus mean transpose theta inverse x minus mean. So this guy is now the objective that we would be maximizing. You can differentiate and equate it to 0. And when you do that, you come up with your familiar formula for the mean and variance of the Gaussian, which is that the mean of the Gaussian is simply the average of all of the samples. And the variance is simply the average of the centered second moment of all of the samples. This is your standard variance formula. This is the standard mean formula. And if you ever wondered where it came from, it's a maximum likelihood estimate of the mean and the variance when you model the distribution of the data as Gaussian. So is this making sense? You with me so far?
Yeah.
Okay. So the same thing with Laplacians. A Laplacian distribution has this form, 1 over 2b e raised to minus of x minus mu, b, where mu is the median. It's also the mean, but in the case of a Laplacian, it's best assumed to be a median. And then if you have a collection of data, the log probability of the collection of data is going to be, the sum over all observations of the log of this term, which is simply minus x minus the magnitude of x minus mu over b. If you maximize this with respect to the mu and b, you will find that mu is the median of your training data. And b, once again, is simply going to be the average value of the magnitude of x minus mu. And again, this just looks like a counting formula. You get a nice closed form solution. So in all of these cases, when we actually go through the maximum likelihood estimate, we end up with nice counting-based formulae for the parameters of the distribution. But there are other distributions like this one, the Dirichlet distribution. The Dirichlet distribution is a probability distribution over probability distributions. So if you consider category distributions, let's say the roles of a die. At the role of a die, the probability distribution of a dice is a 6-component vector where all the components are non-negative and sum to 1. Now, the set of all possible vectors of this kind is the set of all possible probabilities for the dice. And so we can define a distribution on that set. And a Dirichlet distribution is a distribution of that kind. It has this ugly formula over here. And then if I give you a large collection of these probability vectors and ask you to estimate the parameters of this Dirichlet distribution, you get this, once again, you get this ugly formula over here with gamma functions and such like. And in this case, the parameters of the Dirichlet distribution of these alphas, there's no way you can actually get a closed form for the alphas. You have to solve for this using gradient descent. So unlike the Gaussian, Laplacian, and the category distribution, here is a case where even the simple maximum likelihood estimator ends up needing complex gradient descent solutions. And there are other kinds of distributions where even that is going to be difficult. So in general, again, the idea is that if you have some data, you want to model the distribution of the data, you come up with a parametric model. You use you state the probability of your training data in terms of this parametric model. You state the log probability of your training data in terms of this parametric model. And then you maximize that log probability with respect to the parameters of the model. And that is going to be your best guess for the model parameters that best explain the data. And again, this is based on the hypothesis that the world is very boring. And so we can assume that whatever we've seen is very, very normal for your distribution. Here's a point. Okay, 10 seconds, guys. All right, let me end this poll. Here's what you thought. Let's ask you guys the question. The true model that generates any data set is always the most likely model. Is this true or false?
True.
Is it true?
Not necessarily.
So this is the assumption. We make an assumption that the data that you see is very typical of the distribution. Is that assumption always going to be true?
No.
Right. So for example, if I flipped a coin 1,000 times, there's always the odd chance that I get 1,000 tails, right? Even for a fair coin. And so your assumption that the data that you've observed are very typical is not always strictly true. And so the first statement is false. What about the second one? Maximum likelihood estimation reduces to simple counting like solutions in many cases. True or
True.
false?
True.
True. In many cases, it does end up as a counting-based solution, right? So the first one is false. Not all cases, many cases. So far, so good. You guys with me so far? Because now we're going to go make it more complicated. I know this wasn't the clearest start to a lecture, but this was the easy bet. So I'm assuming it was good. I'd like to see some 10 thumbs up out of the 22 of you so I can proceed. So can you just give me some thumbs ups, please, if you got it? Otherwise, ask away. I have 6. Okay. So let's make this a little more complex, right? So now here's this guy. He has a coin and he has a dice. He rolls the dice and he flips the coin, right? And if the coin comes up heads, then he simply calls out the number that the dice rolled. But if the coin comes up tails, he calls out that number plus 1. Given these outcomes, how do you estimate the probability of heads for the coin and the probability distribution for the dice? Any ideas? In the standard setting, if you didn't have the coin, if you just roll the dice, then if I asked you what's the probability of 3, you're going to count the number of 3s divided by the total number of trials, and that's your guess for P of 3, right? But now here's a twist. He flips a coin, and sometimes the coin comes up head, sometimes it's tails, and the coin may not be fair. If it comes up head and the dice rolled a 3, he'd call out 3. But if the coin was a tails and the dice rolled a 3, he calls out a 4. Based on these, how do you determine the probability of heads and the distribution for the dice? Anyone? Any guesses? Okay. Here's a slightly more complex one. This guy has 2 dice and he rolls them. But instead of giving you the outcomes of each of the dice, he just tells you the sum. So he says the sum is 9. From this collection of outcomes, can you decide what can you take a guess as to what the probability distributions for the individual dice are? And if so, how would you do it? Firstly, do you think it's possible?
I mean,
So you
outcomes
just
would be a
complete.
lot, right?
So the outcomes are he's just calling out the sum. So how would you go about it? Any ideas? Anyone? Does anybody want to take a guess? Can I call up some names and ask you guys? Okay. So I'll wait a few seconds. Can someone suggest something, Isaiah? Do you have any
So
ideas?
what I would do is I'd make like a table of all of the like a joint distribution table of all the possible outcomes, and whenever he says some sort of sum, I would just like I don't know, give an arbitrary +1 to all of the different like intersecting squares, and then eventually I'll just like once I've gotten a really large number of outcomes, just normalize the table and say that's my estimated distribution.
Yeah, but that's a pretty good idea, right? But the point is, different outcomes are going to be counted different number of times, right?
Correct.
Because if you got a 9, there are many combinations which will give you a 9. So you're going to put a +1 to all of those. Whereas if you got a 12, there's only one, and that would only count once, right? So,
Yeah.
okay, it's not easy, okay? Or here's something more complex. I have two guys rolling dice in a room, and you can't peer into the room. There's a guy at the entrance to the room, and he calls out numbers. Each time, he's randomly looks at one or the other of these two guys and calls out the number that that person rolled. So sometimes he's calling out the number rolled by the blue dice. Sometimes he's calling out the number rolled by the red dice. He doesn't tell you which number he's calling out. Whose number he's calling out. He just calls out the numbers. And from this set of numbers that he's calling out, some of which are from this one and some are from this one, can you determine the probability distribution for both the dice? Again, how would you do it? Anyone? Any ideas? Let me ask somebody else, right? So Lucy, do you have any ideas?
Um, does it also depend on how if the both dice are evenly distributed or
The dice are there, the dice are not fair. So anybody else who wants to take a guess? Cynthia, you?
We'll have to make an assumption in this case, right? We'll have to assume at the start, at least he did for green, and then the
You're
next
not
one.
making any assumptions. So Cynthia, do you have any ideas?
Would it have anything to do with like the prior dish? Oh, I was
There's
thinking
no
using
assumption.
Bayes'
Yeah.
rule, but I'm not sure.
Okay. So anyway, you guys are sort of getting there, but let's keep making this more complex, right? Here's a more complex problem. This guy in the box, he has a bunch of Gaussians, a red, a green, and a blue. And then he also has a dice. In this case, he's got a red, green, blue, and a yellow Gaussian. And he's got a 4-sided die. And in each experiment, he rolls the die and uses it to decide which of the Gaussians he's going to use, and then picks up that Gaussian and draws a sample from it. And then he just calls out the samples. So all you've got are the samples being called out. You don't know which Gaussian any of these samples came from, and you don't know how he selects the Gaussians. Given this, how would you determine the probability distribute the parameters of the individual Gaussians? Ideas? Guru, what about you? Any ideas?
You could only determine the posterior probability, right? You couldn't.
You don't know anything about the data, right? So posterior of what?
So okay, so then it's impossible, no?
So here's how we're going to do it, right? So the issue was that in each of these problems, there was some information missing. If this information were available, estimation would have been trivial. What is this estimation information? Let's look at it. Let's look at missing information. There are two different kinds of missing information. The first is missing information about the underlying data. The second is missing information about the underlying process. So let's look at this first guy first. Missing information about the underlying data. So let's say, we've already seen this very trivial problem earlier. How do I compute the parameters of a Gaussian given a collection of independent observations from the Gaussian. The mean of the Gaussian was simply the average of all of these samples. The covariance matrix of the Gaussian was simply the center outer product, x minus mean times x minus mean transpose. You took the average of this over all your training samples, and that was your covariance estimate. And it's very simple, counting based, right? Trivial. But here you're assuming that the entire data X is given. And keep in mind that this is based on the maximum likelihood principle, which is maximizing the likelihood of whatever you did observe. That's all you have, whatever you observed, right? But then let's go here. So let's say I have a collection of data vectors, and I'm told that these have come from a Gaussian, and I must estimate the distribution of the Gaussian. Except I have a problem. Many of these data vectors are incomplete. Some of these components have never been reported. In this case, how do we estimate this Gaussian? Now, I cannot simply take the average of all of these vectors to estimate the mean because many of these guys are missing, right? And this kind of data are very common. This particular problem, is very common. It's for example, in recommendation systems. Recommendation systems still work off simple correlations where you assume some sort of a Gaussian distribution. And so let's say you have a movie recommender system. Each of these column vectors could be one user for Netflix, for instance. That user, Netflix has 1 million movies, but any given user has only seen about 100 of those. So you're going to have 100 components for which the user has given ratings. And none for the rest of the movies, you don't have a rating, right? And so every single rating vector for every single user is going to look like this. It's going to be incomplete. And from that, nonetheless, you have to compute the parameters of this Gaussian. So it's not like it's an unusual problem. It's a problem that we deal with in everyday life all the time. So given data of this kind, incomplete data, how can we estimate this Gaussian? Any ideas? Over here? Well, so MLE, right? But let's look at MLE again. P of X is a Gaussian. The original problem we had was estimate the Gaussian given a collection of data vectors of complete vectors, right? And when you had a collection of complete vectors, then the log likelihood of your training data was the sum over all training instances of the log probability of the individual vectors in the data. And this you could differentiate, and you got the mean and the variance. Except in our setting, the data are incomplete. You only observe these guys. The other components are not seen. And so instead of seeing the excess, you're only seeing the O's at each time, where O is the set of observed components. And now we have to estimate the parameters of this Gaussian from the set of observed components, meaning the set of incomplete vectors. And if I use the maximum, and we're going to be missing all of these other components because they were not reported, right? So we will call these the missing components of the data. Now, the complete data, the complete vector is going to include both the observed and the missing components. So if you want the complete data, X, that's for each vector, it's going to be the combination of the observed components and the missing components. Keeping in mind, of course, that the complete data are not available. The missing components are missing. So are these definitions making sense to you guys? The observed components, the missing components, and the complete data. Are these definitions making sense? Yes, no? I'd like to see 15 thumbs ups, please. 10 of them. Now keep going. I have 9, 10. All right. I'm assuming they do, right? I couldn't get 15. I managed to squeeze 11 thumbs ups out of you guys. Now, when I perform maximum likelihood estimation, what must I maximize the likelihood of? Anybody?
The distribution generating the observed data.
the only thing that you have are the observed data, right? So the maximum likelihood estimate can only rely on the data that you did observe. And so your maximum likelihood estimator is going to try to estimate this mean and variance of this Gaussian that maximizes the likelihood of all of these green components, right? Yes or no? And can we compute this directly? Keep in mind that our probability distribution is defined on the entire vector, whereas this is only a part of the vector, right? So what would I need to do? I know that the complete vector is a combination of the observed data and the missing data for each vector. So if I want the probability of just the observed components, I must integrate out, I must marginalize out the missing components from the complete data. So I have to take the integral of this probability distribution of X over the missing components so that I can marginalize them out, and I'm left with only the probability distribution over the observed components. And the log probability of the observed components is what I'm going to be maximizing, which gives me, this is the sum over all observations of the log of the integral of the probability distribution of the complete data, where you're integrating over the missing components. So you have an integral within the log. And so here's what we'd actually have to do. If you were performing maximum likelihood estimation, we would have to maximize the log likelihood of the observed data, which is the sum over all observations, all vectors, of the log of the integral of the probability of the complete data with respect to the missing components. So this now is no longer a simple sum of logs. It's the sum of logs of integrals. Is this making sense? Yes or no?
Yes.
Right. So be a little more enthusiastic with the thumbs ups, guys. I'm not getting past single digits here. I'll wait for 10 the next time around, okay? And so this is challenging because maximizing the log of a sum is very hard. So this was where we were looking at missing information about, we're missing data itself, right? But you can also be missing information about the underlying process. And here, let's take a look at two examples, the dice shooting example and general mixtures. In the dice shooting example, this guy, right? He was sitting at the door to the room, and there were two different guys rolling two differently loaded dice. And he was randomly choosing one or the other and calling out their number. And all you got to see was the sequence of numbers he called out. How do we determine the probability distribution for the two dice? So here, what is the information missing over here? What more could I have added over here, which would have made this problem simple? Anyone?
Which dice generated which number?
Which dice generated which number, right? So again, here there are two distributions. The guy has a choice of picking this or this, and that choice itself is being made according to some distribution. So in each outcome, he randomly chooses the one or the other according to P of K, and then draws a sample from that one and calls out that value. The overall histogram that you see is going to be the histogram of O's, which is going to be this now the sum over all all category distributions of the probability of the observation from that category distribution. Now, differently stated, what is the probability that this guy is going to call out, say, the number 6? It is going to be the probability that he chooses the blue dice, and the blue dice rolls a 6, plus the probability that he chooses the red dice, and the red dice rolls a 6. So it's the summation over all of these distributions of the probability of choosing that distribution times the probability that that specific distribution generated this outcome. So is this making sense over here? Okay. All right. Can I have one more thumbs up just so I get to the number, magic number 10? It's languishing at 9. It's languishing at 9. Guys, those of you who are asleep, do you mind waking up? Okay, I'm going to call him. Sebastian, did this make sense? Sebastian, paying attention? No? Okay. So here, the thing to observe is that the process actually draws two variables for each observation. First, it draws the multinomial, and second, it draws K. It draws the observation O from that multinomial. So the probability of any particular draw is the joint probability of both variables. For any specific draw, there's a two-step process, selecting the multinomial and generating the observation from it. So the probability is P of K times P K of O. This is the probability that the kth multinomial generates the observation O. So to compute the probability for any specific observation, we are marginalizing K out of this distribution, which is why you sum over K. And again, in the ideal case, with every outcome, if this guy had actually told you which dice the outcome came from, then he would just be giving you the color of each number. So he'd say this was a 6, it came from the blue dice. This was a 4, it came from the red dice, and so on. If this information was given, how would you estimate the probability distribution for the two dice? So, Sebastian, can you answer this one? Sebastian Levi. I guess Sebastian Levi is actually absent from class. So, Tianyon, how about you? How would you do this if you had this information?
We can just split into two groups by color.
We can just split into two groups by color. And then, so you have the collection of blue numbers, the collection of red numbers, compute the histograms from both, and just do the counting based estimation of both. Problem solved, right? So this was easy. The problem is that this information is not given. That's why our data are incomplete. The information about which dice generated which number is not both bits of information, but we only have the observation. And so we cannot segregate things, which is why when we're working only off the observed data, you're given the observed data, O1 through ON, you want to estimate the probability distribution for both the category distributions. So you want to maximize the log likelihood of the observed data, which is just the actual numbers you saw. But P of O is summation over K of K times Pk of O, which is the sum over all of the component distributions of the probability of choosing that distribution and the probability that the chosen distribution generated the observation O. And so when I plug this into the formula here, I get the sum over all observations of the log of this term here, which is just drawn from here, where you're marginalizing out the components because you don't know which specific component generated the observation. And so this includes a log of a sum, and the log of a sum is quite impossible to optimize directly. So did this make sense? This entire setup? Yeah. Okay. So 9. Okay. All right. Then so that's the dice shooting problem, right? Let's look at more generic mixtures, like the Gaussian mixture. So here you had this issue where you had a bunch of Gaussians, and each draw you randomly chose one of the Gaussians and then generated an observation from the Gaussian. So the actual distribution says that the probability of obtaining any observation O is the sum over all components of the probability of choosing the component and having that specific component generate the observation O. Now this is a Gaussian mixture because you're mixing Gaussians. And Gaussian mixtures are very versatile distributions. You can use them. They can be used to model all kinds of crazy distributions like this one, for instance. This clearly looks like a mixture of 4 Gaussians, right? A Gaussian here, one here, a third here, and a fourth here. So our objective is to estimate the parameters of all of these component Gaussians from just the observations. Now, again, observe that the process draws 2 variables in generating any observation. First, it chooses the Gaussian, and then it generates the observation from the Gaussian. So the probability of any particular draw is the probability of the end-to-end process from here to here, which is the probability of choosing the, any given draw is choosing a Gaussian and generating an observation from it. So the probability of that is the probability of choosing that Gaussian and obtaining the observation from that Gaussian, which is, so any given draw is a 2-step thing. It's a combination of k and O. The probability of that k and O is E of k times the probability of the observation of being obtained from the kth Gaussian. And so if all I want is the probability of the observation itself, I have to marginalize out k, namely the identity of the Gaussian. And so the probability of any observation is the sum over all Gaussians of the probability of choosing the Gaussian and having that Gaussian generate the observation. Now, here, this is a 2-step process. So if you want to define the generation of the process fully, you would have to specify all the intermediate outcomes as well, which is not being specified here. So if you want to learn the model precisely, you need the complete data, meaning along with every vector, ideally, you would also be informed which Gaussian the vector came from. If you had this information, then how would you estimate the individual Gaussians? Anybody, Ching Sheng, how would you do it if you had this information? If you knew which Gaussian each observation came from? Ching Sheng, how would you do it? Does anybody else want to answer?
I would just separate them into the 3 different Gaussians and then just do our standard maximum likelihood estimator on each of the individual sets of data.
Exactly, right? I can pull out all the blue vectors into the blue group, all the red vectors into the red group, all the green vectors into the green group. And so now the mean and variance of the blue Gaussian can be obtained from this set. Those are the red Gaussian from this set, and those are the green Gaussian from this set. Unfortunately, the identity of the Gaussians that each vector came from is not known. What we want is the combination of the observation and the Gaussian. All we got was the observations themselves. And so here's the situation again. If you were performing maximum likelihood estimation, you only have the observed data. You want to estimate the parameters of all of the Gaussians, but just from the observed data. The log likelihood of the observed data is the sum over all observations of the log likelihood of the individual observations. Again, this is assuming that all the observations are independent. And so we know that the probability of any individual vector is the sum over all Gaussians of the probability of choosing the Gaussian times the probability that the Gaussian generated the observation O. And so the maximum likelihood estimator is going to look like this. Is you can plug in this P of O out here, and it's going to be the sum over all observations of the log of this mixture term over here. And again, so now you have the log of a sum, and optimizing logs of sums is really hard. You cannot use direct optimization. And so we have a problem, right? And so in general, the general form of the problem is this. The presence or the absence of missing data or variables requires them to be marginalized out of your probability by summation or integration. This results in a maximum likelihood estimate of this form, where you're maximizing the log of the marginal distribution, which is obtained by summing out the missing terms. So, and the inner summation could be an integral or a summation, depending on whether this variable is continuous or discrete. And I've explicitly introduced this theta over here to show that these are parametric models with parameters theta. And having the log of a sum, makes estimation challenging. There's generally no closed form solution, and we need efficient iterative solutions. So, is this making sense so far? Okay. 9, 10. Okay. So here's your second poll. Can you guys see the poll? Yeah, obviously.
Yeah.
Okay, 10 seconds, guys. Five. Okay. 18 result, so some 4 of you are not paying attention. Anyways, so here's what you thought. Let me ask you again. Is this first statement true? MLE with missing data yields problems that have closed form solutions, true or false? There are no closed form solutions due to the integral inside the log. But if there were a sum inside the log, there would be a closed form solution, true or false? It doesn't matter whether it's an integral or a sum, right? MLE with missing data maximizes the likelihood of the observations only, true or false? Because that's all you have. What you maximize the likelihood of is what you observed. And the likelihood of the observed data is derived from the complete data by marginalizing out the missing data, true or false? True, right? So we're good with this. Only the last 2 statements are true. And so here's what we have. We get the log of the summation over h. H are the missing terms. H because H stands for hidden, of the joint probability of H and O, where O is the observation. Can we somehow get an approximation to this that's more tractable? That is, without a summation or an integral within the log. Because if we could, then we could come up with optimal solutions. Then we could come up with efficient solutions, right? So this brings us to the concept of a variational lower bound. The log of the probability of O is the log of the summation over H of the joint probability of H and O, where H are the missing terms. Now I can multiply and divide PH of O by some Q of H, where Q of H itself is a distribution, such that the sum of Q of H equals 1. This will not change log P of O. Do you agree? This term over here, multiplying and dividing by Q of H. Give me 10 thumbs ups, guys, so I know you're following. 8, 9, all right. So now, the logarithm, it turns out, is a concave function. And so because the logarithm is concave, we can pull this Q outside the log to get a lower bound. Now, what do I mean by this? For this, let's take a look at log of x. This is what a concave function looks like. It's like a function that's curving downwards continuously. So this is x, this is log of x, and this is what log of x looks like. It's minus infinity at 0, it's 0 at 1, and it keeps curving up like this. Now take any 2 x values, x1 and x2. If I draw a line between log of x1 and log of x2, that's going to be this red curve, right? So over here, the y value is log x1. Here, the y value is log x2. So on this line, at any point, the y value is going to be some q times log x1 plus 1 minus q times log x2. Basically, an interpolation of these two log x values. Is this making sense? This one here. Can you give me a thumbs up? 7, 8, 7. Okay. Now here, let's take any x between x1 and x2, which is qx1 plus 1 minus qx2, right? So it's q times this point and 1 minus q times this point. Correspondingly, the y value is going to be qy1 plus 1 minus 2 times qy2 on this line, which is this guy here. So if you look at the log of qx1 plus 1 minus qx2, which is the blue curve, is always higher than q times log of x1 plus 1 minus q times log x2. So do you see this? Log of qx1 plus 1 minus q log of qx1 plus 1 minus qx2, which is this blue curve, is greater than q log x1 plus 1 minus q log x2. This making sense to you guys? This one here? Yes or no? So only 8 of you. It made sense to the 8 of you. So what about the rest of you? Did this not make sense? Aisha, did this make sense to you? No. Okay. Thank you. So look at this again. I have x1 and I have x2, right? So any point between the two can be written as qx1 plus 1 minus qx2. You agree? Because it's greater than x1 and less than x2. So it's an interpolation between the two, right? If I drew a line, then the corresponding y's are also going to be related in the same manner. So at this x, the value of y value on the line is also going to be 1 q times y1 plus 1 minus q times y2, which is q times log x1 plus 1 minus q times log x2. Is this y value making sense? Aisha and Tianyu. Tianyu, did that make sense to you? Okay. But then look at the log function itself. The log is being computed on this x value, right? That's log of qx1 plus 1 minus q times x2. In parentheses. That's the blue curve here, right? Is that making sense? Tianyu and Aisha? Okay, what about the rest of you guys? That makes sense? And so if you look at this carefully, the blue curve, no matter how you draw a line between 2 points, the blue curve will always be above the red line, right? Yes or no? Okay, which means that log of qx1 plus 1 minus qx2 is always going to be greater than or equal to q of log x1 plus 1 minus q times log x2, right? Yes or no here? Can I see some thumbs up? I'd like to see 10 of those, otherwise I'm going to ask. Okay. Or more generally, the log of a convex combination of x's is going to be greater than or equal to the same convex combinations of log x's. This is just a generalization of this guy. Is that making sense? These two are the same equation, just generalized. Right? So Abhishek, did that make sense? Abhishek? Yeah, okay. So, right. So here's what I can do. Because of the log, I can say so long as these q's, so the thing is these q's must sum to 1 for this to hold. Here I was using q and 1 minus q. The sum of those two is going to be 1. But in the general case, these q's must sum to 1. That's how I get a convex combination of x's and a convex combination of log x's. Okay. So if I look here, log of summation over hq of h times ph over q of h, using the same rule here, I can pull the q out, and this guy is going to be an upper bound on summation over h qh log p over q. Is this making sense? Again. All of you? Okay. Oh, Doreen, did that make sense? Isaiah, yes? Okay. But observe that the left-hand side, I could just cancel out the h's. The left-hand side is summation log h p h given o. So the left-hand side is simply log of p of o. This left-hand side. All I did was multiply and divide by q of h, right? So what we are saying is log of p of o is always an upper bound on, or is lower bounded by summation over h qh log p over q. Is this making sense? Okay. And so this is what the concavity function says. Log of p of o with theta is greater than or equal to summation over h q log p over q. And this will work for any q, so long as the q's sum to 1 and they're positive. So this guy here, it's called a variational lower bound, or an elbow empirical lower bound on the log likelihood of the data. Now, what does it mean to have a lower bound of this kind? This is what it means, right? So look at this theta over here. Both the left and the right-hand side are functions of theta, correct? Yes or no? If you vary theta, both the left and the right-hand side will change. So how, Cynthia, you agree with this? Okay, so I can draw both as functions of theta. This guy here is your log likelihood, this term here. This guy here is the lower bound, this one here. And what it means is that for any value of theta, this blue curve is always going to be below the red curve. Always, always, always. At best, it could touch it, okay? So I can make this lower bound tight. Also, again, look, this red curve is your log likelihood, right? The blue curve is this variational lower bound, which is summation over HQ log P over Q. Different choices of Q are going to give me different blue curves. That making sense? Over here, that if I change the Qs, this lower bound curve is going to change. And so there is one Q which makes this bound as tight as possible, really, really close to a red curve. And that's the Q we're going to try to find. And so what is that Q? Here it is, right? Quite arbitrarily deciding, again, observe that the log likelihood is a function of theta, right? This is the joint probability. This is P of O, which P of O we saw again is way back here. Where did I do that? It's going to be some. And the missing components, except the missing components, are integrated out. Now I can, so this I can write, let me say Q of H is the posterior probability of H given O, meaning given the observed value, what is the probability of the hidden value? In the case of the dice, given the outcome 6, what is the probability that this came from the blue dice? And what is the probability that this came from the red dice? That is the posterior probability. That making sense? What I mean by the posterior probability here? Okay. And that posterior probability is going to depend on the parameter that I have for the model, right? Yes or no? Because different thetas are going to give me different P of H given theta. Again, let me know if you got this, guys. Yes or no? Okay. So for Q of H, let me just say that Q of H is P of H given O when I set the parameter to be some theta prime. And we are trying to estimate theta, right? We are trying to estimate the parameters of the P of O. So I'll say Q of, if I just say Q of H is P of H given O at for theta prime, I could choose Q of H to be anything. I just chosen this. Then I can say log of PO is lower bounded by summation over H, P of H given O theta prime times log of P of H comma O theta divided by P of H given O theta prime, right? So this equation making sense on top. I just plug this Q of H into this formula. Okay. And again, what about the rest of you guys? Making sense? Okay. Observe that now this is a function of two thetas. It's a function of theta and it's a function of theta prime, right? So I can write this as j theta theta prime because theta occurs twice, both as theta and theta prime. Again, do you see this? Yes or no? This one. Some of you have not. Okay. So what this means is that the log likelihood of the data is lower bounded by j theta theta prime. This is one case, right? But then if theta prime were exactly equal to theta, these guys would cancel out. And you're simply going to end up with summation P of H comma O, which is P of O. So in other words, when, actually, this is, it turns out, actually I should be able to plug it in, that if theta equals theta prime, this j theta theta prime simply becomes log of P of O. I should have written the proof over here, it's one line. So we have these two things, which means that here's what we get. I can, and yeah, here's the proof, right? J theta theta is P of H given O theta times log P of H over P of H given O theta, which now P of H comma O divided by P of H given O is just P of O. So this just becomes summation over H P of H given O theta times log of P of O. And the summation over H of P of H given O is simply going to be, this can come out. This is not a function of H, right? This is the probable summation of the probability distribution over all values of H. This becomes 1. So this little proof basically tells us that P of, when I set theta prime to be equal to theta, that just gives me P of O. Is this making sense? So far? Just the math. Okay. So how does this help us? I have j theta theta prime is sum over H, P of H given O theta prime log PHO divided by P of H given O. I have found that this is a lower bound on log P of O. And when theta equals theta prime, this is just P of O. And believe it or not, this is enough for me to give me an iterative algorithm that guarantees non-decreasing P of O with iterations. All I have to do is set my initial value of theta, and at each time I just fix the theta prime to be theta k and maximize this over theta. And that new estimate of theta is going to be, the resulting theta is going to be my new estimate of theta, which I can plug right back over here and keep iterating this process. And if I keep doing this, I'm going to keep increasing log of P of O. So how does that work? This is how it is pictorially. So let's say I have j theta theta prime. This is defined, right? So let's say I took some initial value theta 0 over here. If I had some initial value theta 0 over here, once I fix this, then I know that this guy here is not only a function of theta, because theta 0 is fixed, and it's going to be some curve of this kind, j theta theta 0. This is my log likelihood for my observed data, which is also a function of theta. Now, when theta takes the precise value theta 0, I end up with j theta 0 theta 0, which is log of P of O when the parameter is theta 0. So is the fact that this is a lower bound and that at theta 0, the two curves touch, making sense? So what about you? How? Aisha, is that making sense? Okay. And so now I have this, right? Once I do this, I can just find the place where j theta is maximum, which is over here. I call this theta 1. This is my new estimate for theta. Now I can construct a new j with theta 1 out here, okay? And so the new j is going to be j theta theta 1, and that is guaranteed to touch my curve at theta 1. I can maximize this guy again, right? And this is going to be my new estimate for theta, theta 2. And now I can construct a new j, which with theta 2 out here, and that's going to touch my curve right here. And I can maximize that with respect to theta. That's theta 3. And then I can construct a new j with theta 3 on the right-hand side. And that's going to be this curve, which I can maximize, right? And I can keep repeating this process. Is this making sense? This whole process over here, what we just did. Pictorially. So, all right. Mayur, did that make sense? Prem Sai. Okay. So that's basically all the algorithm is, right? You're going to initialize theta 0. Then you construct this elbow function, also called an auxiliary function, which is this summation over O, the expectation over the posterior probability of H given O using the current estimate for the parameters of the log of the joint probability of H and O. So you'd stick theta 0 over here, and you get j theta theta 0, you maximize it, then you get theta 1, then you stick theta 1 over here, maximize the resulting j with respect to theta, and you get theta 2, and so on. Right? So again, here I have P of H given O divided H comma O divided by P of H given O, and the denominator still has theta k. I can say log of the ratio of two terms is the log of the numerator minus the log of the denominator. So I can separate it out like so, right? This is the summation over O of the sum over all H's of basically the expectation over the posterior of H computed using theta k of the log of P of H comma O, which is this numerator, minus the same expectation of the log of P of H given O with theta k, which is this denominator here, right? And this term is not a function of theta. There's no theta here, just theta k, right? So I can ignore it for maximization. And so I can just keep this first term, and that is sufficient. And so that's what I will do. I'm going to keep iterating over k. I initialize my thetas. And until the log likelihood of my data converges, here's what I will do. First, I'm going to compute the posterior probability of H given O using the current estimate of thetas. This is my expectation step. And then I can plug it into this objective function where I'm summing over all the observations, the expectation of the log probability of log of the joint probability of the hidden and observed data with theta as the parameter, where the expectation is taken over the posterior probability of H given O. And so this is the so-called expectation maximization algorithm. Our objective is this one here. We want to maximize the log probability of the observations, which is the log of the marginal of over the hidden variables. of the joint probability of the hidden and observed variables. And this we would do by the simple iterative estimate, where at each time you're basically maximizing the expected log of the joint probability of the hidden and observed data, where the expectation is taken with respect to the posterior probability of the hidden variables given the observed variables, where the posterior is computed using the current estimate of the parameters. This guy here, it maximizes an empirical lower bound and guarantees increasing log likelihood with iterations, basically giving you a local maximum log likelihood estimate for theta prime, because every single step over here, as we saw over here, if you keep following the process, as you keep going up at the current theta, the value of the red curve is always going to be, it's never going to be less than the value of the red curve at the previous theta. So it's guaranteed non-decreasing. In fact, it's going to be kind of guaranteed increasing. And so if you just follow these iterations, the log probability of the data keeps going up, and you will end up with a locally optimal estimate for theta star. So the expectation maximization algorithm, in summary, you construct this auxiliary function, which is this term here, expectation of the joint log probability of the hidden and observed variables. And you basically iteratively keep maximizing this Elbow function. And you're guaranteed to get a locally optimal estimate for theta. So this is our EM algorithm, just repeating it all over again. So here's a final poll before I close. Please do we'll take 15 seconds on this, and then any responses? Can you see the poll?
Yep, we can see the poll.
Okay, 10 seconds, guys, because we're running over, please. All right, let me end the poll. Here's what you guys thought. Let me ask this. EM iteratively estimates a tight variational lower bound on the likelihood function and maximizes it with respect to the parameters. True or false? True, right? And we could alternately compute a tight upper bound and minimizes. Is it true or false? No, you don't want to be minimizing anything, right? Lower bound. Okay. So we have, I just gave you like 90 minutes of math. How many of you really understood or got any intuition out of this math? Give me a thumbs up if you did. Okay. You don't have to. Let me assure you that when I first went through this math, I never understood it. I could regurgitate the math, but it doesn't really give you a mathematical intuition for the objective. But really what is happening here is not clear. And so in the next class, we'll actually look at this in a very much more mundane way. We'll skip the math, or we'll have some math, but much less of it, and we'll figure out what really happened. So any questions? So I can go over the poll questions. Let me stop the recording though first.